In this tutorial, which is related to Project 2, we're going to process a few different foils simultaneously and have a look at a few different planforms. So for the project, we're redesigning the swing. The conditions are a cruise condition. The speed is 75 meters per second. These are all stipulated in the project. 1,400 kilogram mass of the airplane. Planform area is 16.2 meters squared. And with a density of 0.996 kilogram per meters cubed, and this results in a lift coefficient of 0.3. The kinematic viscosity, which we'll need for the Reynolds number, is 1.74 E minus 5 meters squared per second. And what we're going to do is look at a couple different foils, a 23012, an Epler 207, if I can find where I put that on my computer, a 2412, which is the original foil of the airplane. And we're going to look at a couple planforms, I guess just two, a taper ratio of 1 with a span of 11 meters. The root chord and tip chord for that are the equivalent because it's a rectangular wing, a taper ratio of 1. And I'll need to know a few things prior to starting this in order to set up the polars, establish what I need for the polars, namely the Reynolds number and lift coefficient. So we have this lift coefficient here of 0.3, when XFLR5 is doing the viscous solution, it's going to be querying the polar database for each of the individual sections that make up the planform, which will have their own individual lift coefficients and Reynolds numbers. Now the lift coefficients of those sections will not deviate greatly from the lift coefficient of the whole wing. It'll be slightly more, say at the most 50% more, and down towards 0 at the tips. And so I need to be able to have a range of lift coefficient for my polar of, say, I would want to say 0 to 0.5. I also want to have the right range of Reynolds numbers. So I have for my rectangular wing, taper ratio 1 and a taper ratio of 0.3. We'll also look at with the same span. We have a variety of chords. So the chord is constant on this rectangular wing. The chord is not constant on this tapered wing, so it ranges from 0.679 to 2.265. And so I can compute Reynolds numbers for these. One interesting, useful sort of metric is the Reynolds. We have the Reynolds number, which is the velocity times the chord divided by the kinematic viscosity, and I can compute just the velocity over the kinematic viscosity, and this will essentially be the Reynolds number that I'm going to get per meter. If I multiply by a chord of 1 meter, so this is 4.31 million per meter. So if I multiply by a chord of meter, my Reynolds number would be 4.31. If my chord was 2 meters, it would be twice this. It would be 8.6. If the chord was a half meter, it would be half this, which would be 2.15 million. So by knowing this number, I can just simply multiply this by any of the chord lengths in meters, and I will get the Reynolds number. So for this rectangular wing, we have a Reynolds number about 6 million. For the tapered wing, it ranges from 2.93, well, I guess 9.76 at the root. That's the highest Reynolds number we're going to be seeing in any of these simulations, down to 2.93 at the tip. So I really need about 1 million, we'll say, to about 10 million will be my Reynolds range that will run for these foils. And the last thing I'll mention, once I get there. So I'm going to launch XFLR5, and hopefully this is showing up in the recording window. And what I'm going to do is start off by running a direct analysis, X-foil direct analysis. And we'll grab the NACA 2412. Now the XFLR5 can internally do NACA 4 and 5-digit series. So I'm going to grab those. I can't remember what I was going to use. 23012, 2412. So the project stipulates a 12% thick foil. So this is a 12% thick 5-digit foil. This is a 12% thick 4-digit foil, and the E207, which I got from the UIUC airfoil database, is 12% thick. So it's an Epler foil. Design NACA foils. I'm going to grab the 2412. I am going to set this to 150. Points around the perimeter. Okay, and it will use the clustered spacing automatically. I hit OK. So I've loaded an ACA 2412. I'm going to grab a 23012, I believe it was. 23012, that's a 5-digit. 150 again, it's not a particularly aesthetically pleasing foil. Okay, okay. And now I'm going to load, if I can find it, I'm going to open, and oh, there it is, right there, E207 DAT. Now this was downloaded from the UIUC database. It's in the format we need for XFoil, which is let me just grab the data. I'll open it up. Let me open up in a terminal here. Foils. I can find where I put it here. Let's open up here. Outbox documents, courses. Too many things on this computer. Where is that? Okay. So I'll just VI that data. So open it up in my VI, the editor I use, and so the header is just the name of the foil. This is only going to be used for naming things inside the system, as it is in XFoil. It doesn't affect anything else. And then you have two columns: trailing edge X, X column of X, column of Y. Starts at the trailing edge, moves backwards on the upper surface. Upper surface, you can see the Y coordinates are all positive, so we're on the upper surface going backwards towards the leading edge, which is right here. We're at the leading edge, and now we are moving back towards the trailing edge on the lower surface. You can see the Y coordinates are all negative to the end, back to the trailing edge point. So that's in the correct format, so that should work. Let me close that, load it into here, open. Okay, so we've loaded the foil. It's probably not easy to see. I'm going to right click on here for current foil, set style. Let's pick a color that's a little more obvious. How about this pink? And line width, which we can see. Okay, now you can clearly see that. And we will, this gets imported. I think there are maybe 50 points in the actual data, and we need to redistribute. So here I go to design, refine globally, and you can do, fancier stuff if you want, but we just need to refine globally. We're going to switch the number of panels. It looks like there was 61 points in the raw file, up to 150. When I hit apply, you'll see the clustering that will occur here and refinement, hopefully. Okay, done. And now I say okay, and I'm going to save it. And now we have an existing E207 in here, which is the one I imported with the lower resolution. And I'm going to hit OK. It's going to ask me if I really want to overwrite that one, and I do, yes. So I do. So now I have 3 foils in here that I can work with, and I'm going to do an analysis on these. I may pause the recording depending on how long this is going to take. I'm going to do analysis. I can do a multi-threaded batch analysis of these foils, and I need to put in select foil list here. So by default, it's current foil only, which happens to be the Upload 207, but I want to process all of them. So I click foil list. Here I select them all. I guess I could have hit select all here. Okay, so we have all foils in here. It says foils to analyze, and it gives you a little list here. Now I need a Reynolds range. I'm going to do a million. Actually, it looks like it's set up to go. So I'm going to do a million. I want to make sure that's right, to 10 million here. In increments of 500,000, this is reasonable. Now, if you have a wing, and if you look out here, our chord put us of 2.2 meters, puts us just shy of 10 million. If we happen to use a slightly lower taper ratio, let's say 0.1 or 0.15, with this span, we would end up with a root chord that's more than this, say 2.5 meters, which would result in a Reynolds number of, say, 12 million. And you'd say, okay, I need at least 12 million. There is a hiccup in this program in that it doesn't appear you can put that number in here. So if I put 1.2 e to the 7, I'm not able to do that. So I can put 20 million, and that would certainly be suitable. It's much higher than 12 million, but I can't put 12 million. So I can put 10 million or 20 million, but not 12. So just make sure this range covers your full range of Reynolds. So here, 1 million to 10 million is suitable. If you had to go above 10 million, you'd have to do 1 million to say 20 million if you had a long cord. Then don't touch the mock. The end crit, stay 9. This is related to the free stream turbulence level. This is suitable. And no tripping of the boundary layer. We'll let XFoil handle that. And in here we specify the range. I always use alpha, but theoretically here we could do a CL of say 0 to 0.3. Actually, we want to go a little higher than 0.3 because the wing lift coefficient is 0.3. So there will be some sections that are probably going to be closer to 0.4. Some as low as 0. -3 to 10 should cover that range, so I'm not concerned about that. We're going to get 0 lift or negative lift. We will certainly get lift coefficients above 0.3 with angles of 10 degrees. We don't need to go all the way to stall in this case because our lift coefficients are not that high in the actual 3D wing. So I'm going to leave this as it is from -3 to 10. And I'm going to use 2 threads because I have 2 cores on this little laptop. And I think that's all I want to do. So I hit analyze and I'm going to pause the video while I'll let it go and then I'm going to pause the video. So it's going to start running. And it's essentially processing, it's doing the 2412 first. It looks like it's doing 10 million, 9.5 million, 7.5, actually it's going pretty quickly, 4, 3.5, 3 million, 2 million running. And each of these Reynolds running all those angles of attack. 9.5, now it's doing the 23012 foil, 8 million Reynolds, 7.5 million Reynolds, 7. And so some of these, it goes faster, some of these go slower. Depending if it's hitting some hiccups in convergence and whatnot, but it's going fairly rapidly, so I'll let it go. So we're down to 3.5 million in the 23012, 2. It's almost done with this foil. Moving on to the Epler in a second. 1.5 million. Okay, we're now on the Epler. Now 9.5. So it's doing each of these files one at a time, running backwards through the Reynolds numbers because I think you get better convergence at higher Reynolds numbers, and therefore it starts off with a little bit better initial solution. So it's spanning this whole range of alpha for this whole range of Reynolds for all 3 foils, and provided when it's running the 3D case, when it goes to do the viscous assessment, as long as the lift coefficients fall in this range, we're going to have a look at that in a second. Here we see that I'm looking at this, the Epler and the 2412 have very similar lift lines. I think their cambers are quite similar. Slightly lower camber for the 23012. Actually, no, I had that backwards. This is the 2412. This is the 23012 and the Epler. You see the lift lines are fairly Reynolds insensitive. And the key thing looking here is I want to make sure I'm getting a good range of lift coefficients. So I'm getting negative lift coefficients here all the way to lift coefficients of 1.2. The range I really need is right here, basically 0 to 0.4, and my data clearly spans that range, so I don't have any concerns about this, and I know my Reynolds numbers will be sufficient. So that's done. These polars are in here. I'm just going to save this for now, so I do File, Save Project Is. I probably have something in this folder. I'll just overwrite that. Test. Sounds good. Replace. Okay, so that's saved. Down here it says the project's been saved. The name's Test. And now we're going to build a wing. So the first wing, let me just have a look at it, is a tape ratio of 1. Root and tip chord are both 1,473, and the span is 11. So we'll go File, Wing and Plane Design, Plane, define a new plane. Plane name, I don't know what we'll call it. We'll call it rectangular wing. And what foil should we use for this? We'll use the 2412 for this. 2412, I want to deactivate elevator and fin. So this is designed for building a whole plane, including the fuselage, which it warns you really not to do. The fin and elevator, which are both parts of the tail, we don't need that. We're just doing main wing in this case. So deactivate these, otherwise you'll have an issue. Main wing is on by default. I'm going to go define that. So this was, again, what did I call this? I already forgot what I call this, rectangle 2412. Now, I'm going to put in a half span, so I'm defining a symmetric wing. Is that spelled wrong? Symmetric wing, and I'm going to define half of it, and it will just symmetrize it for me. by default, it's sort of a micro scale wing, so I'm going to boost it up here. I've already forgot what this number was, 1473, and like that. Ooh, that's interesting looking. 1473. Okay, so it's rectangular. It has, by default, a little bit of sweep to it. So I'm going to change the sweep, and I can see this is running out of the recording window, so let me pull this up a little bit. And offset here, so by offset, if I offset this a meter, you can see what happens. So that's essentially the position of the leading edge of the tip relative to x, and the root starts at x equals 0. I'd like the tip start to x equals 0 in this case because it's rectangular, no dihedral, no twist. I'm going to pick this 2412 foil for both wing root and tip, and you can see the foil right there. If I left click, is it left click? Yeah, left click command, at least in the Mac. On the Windows, probably left click control, I would bet. I can orbit this around, rotate this around. I can see what it looks like. And I want to change the paneling to 25, 25. And that will be enough so I can get a decent solution. If I were doing a real design, I would probably boost this, but the expense of the computation goes roughly as the square of the number of panels. And so if you were to double X and double Y, you've now increased the number of panels by 4, so you've increased the computation time by 16, and so it goes up very quickly with these panel increases. So I want to keep a reasonable computation time, so 25, 25 panels we'll have a look at, and you can see that they're distributed by default using in the X direction a cosine distribution, which bunches at the leading edge, bunches at the trailing edge, and in the Y direction a minus sign distribution, which has bunching at the tips and not bunching at the root. That noise you hear is my cat. And so let's keep that, and we will hit, I just want to double check everything's okay. That looks good, and I will check here the area comes out right, 16.2, and that is correct. That's the project area, Planform area. So save and close. This is done, hit OK. Now I'm going to do an analysis of that wing. So you can see the wing selected here. I have this only this one wing defined. I'll do define and analysis. It tries to name it something useful. I don't know how useful this is. This auto analysis name, you might try to come up with something better based on how you're filling out your Excel spreadsheets, but I'll just leave it for now. So we're doing a type 1. So this is fixed speed, fixed flight condition, 75 meters per second. We're going to use the VLM2, leave the Viscous on. And so it's not a true Viscous solver. It's going to run the inviscid solver, and then it's going to do a Viscous estimate for the profile drag based on X-foil. It doesn't have any feedback to the actual pressure distribution and therefore induced drag. This is an add-on. I would consider this an add-on. Inertia, I'm going to put in the plane mass here, which is 1,400 kilograms. Oops. 1,400 kilograms. Reference dimensions, we don't need to change. And finally, the aero data is 0.996. I want to just double check that. 996 for the density and 174 E⁻⁵ for the kinematic viscosity. That's correct now. And I just want to run back through, make sure everything is on the up and up. So you polar. Okay, so that's ready to go. Now I'm going to do an analysis. So there are a bunch of different options for XFLR5, which are these things, and you can read about them online on the main website. They describe what these are, and they're really for doing polars of the 3D wing and to look at the entire design space. For what we're doing, this single operating point, there isn't really a specific approach for that, so we're going to sort of hijack one of these to make it work for us, which is the fixed speed. So what I'm looking for, actually it's asking me to overwrite, but we've done nothing, but that's right, that's okay. And so I'm guessing somewhere around 1.5 degrees is necessary for the right lift coefficient. We'll find out. Analyze. Okay, so we're getting the lift coefficient of 283. We switch to the 3D, the 3D view. 283, so we're a little low. Now I could take the lift curve slope, which is roughly 0.1 per degree, and do a little math here to figure out how to get that additional 0.17 CL, but allow me to be lazy and just do it this way. 290, I'm getting, if I put 1.7 degree, 298. So that's close enough. So there's 298 is my lift coefficient. I'm looking for you to get between 298 and 302 to be at least consistent. And in this 3D window, as I show in the other video, you can look at some important stuff, which is the transition. This is the upper surface. You can see the transition on this upper surface is about 50% of the chord at this Reynolds number. You're getting, it's pretty close to 50% of the chord is where you're getting transition. The upper surface, you can look at the lift distribution. It's a nice looking lift distribution. It's not quite elliptic, it's a little overloaded at the edges, I can see here. And that's because we have a lot of chord at the tips versus a true elliptical wing or even a tapered wing. There's a lot of lift, more lift than needed being produced by these tips. So it's overloading the tips, and associated with that, you should also see the downwash is increased at the tips. The downwash, again, for an ideal wing for minimum induced drag, has a straight constant downwash all the way across. Clearly that's not the case here. So we have a non-constant downwash and non-elliptic lift distribution. So our induced drag for this aspect ratio will not be minimum, but we knew that because we're using a rectangular planform with a taper ratio of 1. You can also look at some quantities again in this window. These are span-wise distributions. If I double click here in this window, I get lots of options. For example, the bending moment distribution I can see here is peaking at the root, decreasing towards 0 at the tips. And I see my max bending moment here, and I can dump this to data to find out the actual value, but it's about 15,700. So this is exceeding my project stipulation of 15,600. I'm exceeding that, and I think because I used a rectangular wing with extra loading at the tips, it caused the bending moment to go above, slightly above, but above the threshold that constraint for the project. So according to this and our 12% wing, it would break according to our project description. So, but it's close. It's pretty close. You can also look at, I like to look at the viscous drag coefficient. So this is, let me actually go back here. So when it's done with, the induced, with computing the pressure distribution on the wing, which allows it to compute a lift and an induced drag, it then goes and, because we selected the viscous option in the solver, it will then try to get the profile drag. And so essentially think of each of these as a separate wing section. And each of these wing section has its own lift coefficient, which looks something like local lift coefficient distribution looks like this. So you can see the average wing lift coefficient is 0.3 because we set the angle of attack, so we got exactly 0.3. And you can see sometimes it's above, it's high as 0.35. My window's getting cut off here, hang on. It's as high as 0.34 and as low as getting close to 0. It doesn't go exactly to 0. 0.02, so essentially 0. So 0 up to slightly more than what we want, what the whole wing coefficient is. And so in addition to the Reynolds number, which we pre-computed because we know the chord and flight speed and kinematic viscosity, we know the Reynolds range for this aircraft, which I can also plot here. I think that's one of the options, Reynolds. So there's the Reynolds range. It's rectangular, so there's no range at all. It's just a constant Reynolds number that's equal to that 6.35 million that we had pre-computed. This is being computed within XFLR5. So my polars have to encompass the Reynolds range, which is just a single number, and has to encompass the CL range, which is roughly 0 to 0.3, whatever, 0.34. And so that's, as long as our polar encompasses all that data, then when XFLR5 goes, and for each of these sort of pseudo wing sections, it has a lift coefficient, which varies over the span from a little higher here to 0 at the tips. Has Reynolds number, which in this rectangular case doesn't vary at all. It takes that Reynolds and lift and runs to XFoil for this particular foil section, the 2412, and asks it, where is the transition, upper and lower surface? What is the viscous pressure drag? What is the skin friction drag? And it adds it into the total drag. And so here it's reporting the total drag coefficient and total lift coefficient on the screen. I don't like the number of digits used here. I'd like to see an additional digit for accuracy, but This is suitable just sort of for checking. It also produces, interestingly, this CL over CD, which is a nice thing to report. And this efficiency. This is the E planform efficiency being computed automatically here. And so it's being computed using, I think I threw the equation in here. So we have our induced drag is equal to CL squared over pi aspect ratio times this planform efficiency, which is equal to 1 for a elliptical lift distribution. So we can solve for E in terms of these quantities. So right now, XFLR5 is computing our lift coefficient. Actually, we're setting it so it's exactly 0.3 squared. Pi is pi. The aspect ratio is just based on the geometry of the wing, in this case b squared divided by s, or b over c, because our c is constant, times this induced drag coefficient, which is computing, to give an E right here. And that's what's being reported here. It's roughly 98%, or 0.98 is our planform efficiency. You may see efficiencies greater than 1. It is possible. It seems like it would be impossible, but keep in mind that the induced drag isn't 100% accurate, and Prandtl's theory is based on thin wings, infinitely thin wings at small angles of attack, and we have here a finite thickness wing, so it may not obey this exact relation. But it's still a useful quantity for comparing wings, because as you improve the efficiency here, that will mean that your induced drag is decreasing for a given aspect ratio. We can also look at more accurate values if I go up to current operating point properties, and I can see here I have these values, which I'm just going to actually copy and paste under our wing here. CL is 0.9834, so that's what we set it for. Basically 90 counts, 91 counts of total drag, which consists of 52 counts of viscous and 38 counts, or 39 counts almost, of induced drag. I'm going to stick this right here. This isn't the most organized thing here, but that's okay. So, so right here, so I have my 2412, so that's taper ratio 1. Produce this data here, and I say OK, and I can also dump this to, if I want to dump it to, export it to, save it as a text file. I'm going to hit save. I already have something there called this for some reason, but that's okay. 1.7, that produces this kind of data. Let me grab that if I can find it here. Foils. Is it this one? Yes, 11:39 p.m. So it's this one. Okay, and it has all the data, all the pressure distribution from every single panel on the wing. So that's a lot, but you don't need all this. What we'd want to look at in particular is the max bending moment, which is reported here, and I can see it's higher than the 15,600, which was reported for. This is really a messy way of doing this, for the project constraint. All right, so that's done. Let's swap out, let's maybe make a new wing. What should we do here? Why don't we'll use the same foil and we'll make that other wing. So I can say File, and I'm going to do another wing in plane design. Actually, we're still in that menu, so I'm going to just do plane, define a new plane, and I'll call this, what should we call this, taper ratio. What is the taper ratio? 0.3, so I'll call it 0p3 with a 2412. I'm going to copy this. Again, deactivate elevator and fin, define the wing, call the wing that, and I'm going to use the same span, so a semi-span of 5.5 meters, total span of 11. I got to check my numbers down here. So I have 2.265 on the root chord, 2.265 on the root chord, and I have here 679 on the tip chord, 0.679 on the tip chord. I'm going to have to set our offset correctly, so I can compute that offset, what I need, by just doing, throw out Python here, and so you say 0.5 times 2.265 minus 0.5, because I want to match up the half chord along a constant line. Zero sweep of the half chord times 0.679 is 0.793 is going to be my sweep. So you take half the root chord and you subtract half the tip chord, and then enter that value here. I'm going to put no dihedral, no twist in this case, and we'll go back to those 2412 foils. Oh, I screwed that up. Hang on. Okay, and we want to up the panels to 25. All right, I think this is correct. It looks good. Planform area is very close to 16.2 meters squared, so that's fine. I'm going to save and close. I'm going to hit OK, and now we've selected this wing, so we'll keep it there. And I'm going to run an analysis on this wing. Analysis to find an analysis. Now, it would have retained my numbers from last time because we're still in the same session. Analysis, I'm just going to double check. That's correct. That's correct. That's correct. Hit OK. And we'll keep the same in an angle of attack that worked for the rectangular wing because it has to be pretty close for this tapered wing. It isn't that drastically a wing. Analyze. And what did we come up with? 0.308. So a little high on the lift coefficient. I'm going to drop this down to 6.9. That's not going to be good enough. Why don't we do 6.2? And we're there. So there's the right lift coefficient. If I look at, for example, let's get out of panels, go back to surfaces and have a look at the transition point. You can see it's transitioning about the half chord, a little forward of the half chord, I would say. The flow is going from right to left on the screen here. This is the leading edge. Let's have a look at the lift distribution. It looks a little closer to an elliptic to me, but not quite. I don't like this. I like the fact that it does look like the tips are unloaded a bit closer to an ellipse, but I'm seeing that the midsection doesn't look quite as loaded as it would be if it were an elliptical lift distribution. And I can look at the downwash, which is more constant. You can see you have lighter downwash in the middle, heavier downwash at the root, and then it goes down to higher downwash at the tips. This is a little hard to get rid of the very tips, but that's okay to make that straight. But I'm getting a straighter across most of the span of the wing compared to the rectangular case, but it is certainly not that optimal constant distribution that we spoke about in class. And I can look at span-wise distribution. Here's the lift coefficient, and you can see it's kind of funky that you're getting higher lift sort of the mid sections of the span. This is half the span here. About halfway out in the wing or a little further, you're getting this peak lift coefficient of 0.3, whatever it is, 0.33. It's actually dropping below, so you're unloading. The root is a little less loaded than the mid span is, and then again falling to 0 here. So quite a bit different distribution from the case of this wing here, which actually looks more like an elliptical lift coefficient. But when we refer to elliptical lift, we actually refer to the lift itself, which I'm not sure it actually produces. Yeah, right. So this is actual. This is showing you the distribution compared with the elliptical case here. So let me go back to the lift coefficient, local lift coefficient. And so this is the rectangular wing, this is the tapered wing, and I can look at the viscous drag coefficient. They're probably going to be pretty similar. So you have a little variation at the end in this case because, not because of CL variation, but because of chord variation. So the chord's dropping, so the Reynolds is dropping, so the drag coefficient is going up. Skin friction drag coefficient goes up with decreasing Reynolds numbers. This is drag coefficient. And so in the middle, it's probably going to be pretty close to our rectangular wing. Yep, the values are very similar because we use the same foil and they're roughly operating at the same Reynolds and lift coefficient. So there's not going to be a lot of variation there. But we'll see some small differences. The efficiency of this planform actually, yes, is above 1. So it's greater than the efficiency of the rectangular wing, so I suspect our induced drag is going to be less. If I come up, make sure I'm in the right operating point. Where did we end this? We actually ended with 1.62. Yeah, 1.62. So you want to make sure you have the right operating point, meaning that the wing section's the one you're thinking about, and you are at the angle of attack that produces the right lift coefficient 0.3. Now I can check my operating point properties. I'm going to copy these, or actually maybe we can just compare them here. I'll drop this down here, make this even more of a mess, and copy this, paste this here. And so just looking, the lift coefficients are basically the same. The drag coefficients is a little bit less in this case. We've gone from 91 counts to essentially 90 counts. So not that much different. Our induced drag has decreased slightly by a half count, and our viscous drag has also dropped as well. So both of them dropped a little bit by moving to the taper, changing the taper ratio with the fixed aspect ratio and fixed lift coefficient, everything else, a fixed foil section. So the only thing we changed was taper ratio. We did get some benefit here. The other thing we might have benefited in, I'd like to check, I'm suspecting we're doing a little bit better in the bending moment. Let me just see here. So yeah, so our bending moment is 14,531,689. I could dump the data to get the exact value, but clearly it's below 15,600. So that's the bending moment for this one. The rectangular one had a higher bending moment compared with this one here. I'm going to put it back to the right operating condition, 1.62. So our bending moment has dropped significantly. Looks to be 14,485. If I come back here and just write that down, 14,485. So what that means maybe is what I could do is say, okay, why not keep this taper ratio and make a higher aspect ratio, meaning extend the span. I could pull the span out to a higher number, say 12 meters or 11.5 meter span. That will increase the aspect ratio, and I will have a benefit certainly of a reduced induced drag if I do that, and may still be within this bending moment limit. Whereas with the rectangular wing, we were already over the limit, so it was already violating that condition, and we would have had to shrink. If we want to keep a rectangular planform, we'd have to shrink the wing down, reduce the span, which would reduce the aspect ratio, which definitely would have a negative effect on the induced drag. In this case, we're below the threshold, which means we can increase the span, increase the aspect ratio, and probably reduce the induced drag more. The reason for this again is because the tips are less loaded. Actually, this is the best way to show this, but the tips out here are less loaded in this case, because I wish it showed the actual lift, which takes into account the cord itself. It does not seem to do that except in the 3D figure. So in this case, the tips are less loaded. I don't know if I can flop between these, but let me pull it this way. So this is a lift distribution from the right angle of attack. I do. The lift distribution from the rectangular wing. You get a lot of force out here pulling up, and it creates this bending moment here. When I go back to this particular case, I have less force out here. The more the force is near to the root. So for the same amount of total lift, I'm getting a smaller bending moment, which means I can increase the aspect ratio of this wing and stay within the limits of the bending moment, and a higher aspect ratio will benefit the induced drag. So this gives a hint that maybe taper is good if you're dealing with these bending moment constraints in particular. And so, how long has this been going on? Let me pause there. Let me stop there. So again, by preloading those foils, I could have used any of those foils in these wings, and I could easily go back and define a new plane, which is a new plane based on maybe the same planforms, one of these same planforms, but switching out the foil. And then I can go and look at what's going on with the profile drag and the induced drag in that case. So if you have a slew of wings you want to look at, wing sections, it would be good to preload them, run them all through the polars so the polar data is there, and then you can start building wings based on that polar data. But in general, if you're considering the two major drag components which we're talking about here, of viscous CD and induced CD, this induced value is much more strongly linked to the planform shape. And the viscous value is much more strongly linked to the selection of the foil. And so you can kind of tease these apart. They are somewhat coupled. When you change the planform, you change the Reynolds number, and that will have some effect on the viscous drag. But it's sort of preliminary analysis in terms of eliminating, I would say, classes of foils and figuring out what might work for foils. You get a sense of what kind of Reynolds numbers you're dealing with. Here we're dealing with kind of like 5 million. That's sort of our Reynolds number. A little higher at the root, a little smaller at the tip. This particular section is about 5 million. The other one's about 5 million. We're around the bending moment constraint, which means that we're not going to be able to drive the aspect ratio too far away from here. And so thinking about Reynolds numbers of 1 million and lift coefficients of about 0.3, what foils do well at those kind of Reynolds and lift coefficients? Is it a 2412? Is it a 2612? Is it the 63 or 64 series, which are on the UIUC database? Is it any of the 5-digit series, which are internal in here? Some of them may have benefit in terms of that particular Reynolds and lift coefficient having a delayed transition, having a lower skin friction drag. And those might be ones you would want to try out on this particular planform. So I would recommend using X-Foil to kind of hone in on the foils that you think are good. And that way you eliminate one design variable so that you're not trying foils with all different taper ratios, aspect ratios, and twists. You can say, okay, these are the foils that are working well. Now let's play with planforms in order to get the induced drag down, and then kind of combine the two after that. That's just a suggestion. Certainly there are other approaches to this design problem, but that's just a suggestion to sort of take advantage of knowing that those drag components are kind of tied to two different phenomena. All right, I'll stop there.